Hi folks, we're going to be talking about derivatives since a few of you had some questions on them, and the main three derivatives that we're going to focus on are the power rule, the product rule, and the quotient rule. Okay, so what happens with each of these? The power rule basically says if you have a power where you say x to the n where n is some integer, so n is a constant, then what you can do in that derivative, you can bring the n down and then you go x raised to the n minus 1 power. The product rule says if you have a product of two functions, so two functions, we'll call them f of x and g of x here, what you do is you take the derivative of the first function and multiply by the second function, then add that to the derivative, or the derivative of the second function times the first function, or the first function times the derivative of the second, whichever way you want to say that. Notice since this addition, it doesn't matter which order you do your derivatives in, as long as you're taking the derivative of one and then leaving the other unchanged. In a similar manner, we have a quotient rule. So there's a product of two functions, you could take a quotient of two functions. The trick to this one, a lot of people actually like to use the phrase, so first off you square the bottom, but then they do the low and d high. So the low would be this g of x, because that was the lower part in the denominator, and then d high, so d high meaning the derivative of the upper part minus, and then they say high, and then d low, meaning the derivative of the lower part. So just the high function and then derivative of the lower part. And you remember this one's actually going to be a minus. And playing with these, just a little FYI, some of the functions that I'll use along the way are the derivatives of the trig function. So the derivative of sine of x is cosine x. The derivative of cosine is negative sine. Those are the main two to know. You can actually produce the rest just by knowing those and knowing the trig identity. But it's not necessary for you to have all these down off the top of your head right away. It just takes, if you practice them enough, it does come naturally. But so you can build to the derivative of tangent equals secant squared. Notice when we take tangent, as soon as we tossed in cotangent, so this is cotangent right here, it became negative instead of the secant squared, negative cosecant squared. So it started with a co, it has a negative in front of it. In a similar manner, when we take the derivative of secant, you get secant x tangent x, but as soon as we put a co in front of that, so the derivative of cosecant, you get negative cosecant x cotangent x. So all your things that start with co have the negative symbols in them, and then basically you're kind of mimicking a lot of the other stuff, with exception to the cosine's derivative. But like derivative of cotangent, you just look at the tangent's derivative and then you slap a negative cosecant squared. So, and same thing for derivative of cosecant, you just look at the derivative of secant and then you put a co in front of each one's. So instead of secant x, you have cosecant x. Instead of tangent x, you have cotangent x, and then you have a negative symbol out in front of there. And last but certainly not least, a couple you may or may not have seen, the exponential and natural logarithm. You can actually expand that. I should say exponential with base e. The derivative of e to the x, that's going to be the easiest one you've ever done, is just e to the x. Okay, so keep that in mind. It just spits an e to the x out. And then derivative of natural log of x, well, this is the trickiest one for a lot of people. It's 1 over x. Okay, so the natural log disappears. And natural log is just the log base e. So if you remember logarithms, that's something you can kind of keep in mind. And we'll discuss those even more at a later time. Right now, we're just worried about calculating the derivatives and doing it a lot faster format than having to take limits. So, without further ado, we're going to try and find the derivative of the following functions. So we're going to start with f of x equals 5x to the 7th minus 3 times the 12th root of x plus 9 over x cubed, and then minus 7. The trick to all these, this is going to be the power rule, obviously I have it listed up there, but the trick to this is rewriting the problem in a format we can use the power rule in. So you have 5x to the 7th minus 3, and then instead of this 12th root of x, let's write it as x to the 1/12th power. That'll be a lot easier for us to work with. And then plus 9 over x cubed. Another way to write that is 9, and then when you have an x in the denominator raised to a power, that's just x to the negative whatever power appears down there, so that's x to the negative 3, and then minus 7. And then if we're ready to take the derivative, here's what we can do. And when you saw before, I didn't mention it, but that d over dx, that means we are going to take the derivative of the function. And I'd strongly suggest using that notation. Not saying you have to, but it does help a lot. So what we can do, constants don't get involved. in terms of our derivatives. So you take 5 times the derivative of x to the 7th, we're going to have to take that derivative, minus 3 times the derivative of x to the 1/12th. And that's the beauty of derivatives, you can always pull those constants out in front. And then plus 9 times the derivative of x to the -3. And then minus the derivative of 7. And by the way, you see a d over dx, that means we're taking our derivative with respect to x. There will be cases later on in calculus where you have to pay more attention to, are you taking the derivative with respect to x or derivative with respect to y, or what variable are you dealing with? So keep that in mind as well. That's why you see an x down below right there. It's telling you what you're taking your derivative with respect to. And if it's not an x involved, that means it's a constant. So in this case, we can break this on down. So you get 5, and then you get times 7x to the 7 minus 1 minus 3 times 1/12 x to 1/12 minus 1 power, which we'll be able to simplify soon enough, and then 9 times -3 x to the -3 minus 1 power, and then the derivative of the constant is just 0, so I'll put minus 0 since we had a minus symbol in front of that. Okay, so now moving forward, what do we get? Well, 5 times 7 gives us 35, and then we have x to the 6th power. 3 times 1/12, that would be 3 over 12, or another simpler format would be just 1/4. And then 1/12 minus 1, so you can write that as 1/12 minus 1. It can be rewritten as 12 over 12. Now you have a common denominator and you could subtract those fractions. So you get x to the -11 over 12, which I can also rewrite in another format too. And then plus 9 times -3 makes -27, and that is x to the -4. So at the end of the day, if we're trying to write down what f prime of x equals, we can fit that in maybe right here. So f prime of x equals 35x to the 6th minus, when you see an x to the -11 over 12, you can put that down in the denominator, so you get 4, and then that 12 in that fraction tells us is a 12th root once again, and then we have an x to the 11th power. And then same thing here, you have, except it's not 27 in the denominator, 27 goes up in the numerator now. So 27 over, and this x to the -4 means it's in the denominator, so x to the 4th. Okay? So moving forward, we can try and figure out g prime of x. The first trick to this one, though, what I'd recommend, is rewriting g of x. Notice in the first case, we didn't mess with f prime of x right away. We simplified f of x first, and the same thing applies here. So what we can do is we can write this as 6x to the 9th over 2x cubed minus 4x squared over 2x cubed, and then plus 9, and that's x to the 1/2 over 2x cubed. And a lot of the tricks are the algebra for a lot of people, so I'll actually kind of simplify that along the way. So this becomes 3 when you take 6 divided by 2, and then x to the, you subtract the exponents, so you go 9 minus 3 minus, you get 2, and then you subtract the exponents once again, so you get 2 minus 3 once again there, and so plus 9/2, and then we'll have x to the 1/2 minus 3. All I'm doing is algebra there. I haven't even touched calculus. The calculus portion is actually the easiest portion here. So now when you get your simplified format, the thing we're going to take the derivative of is 3x to the 6th minus 2 times x to the -1 power plus 9/2, oops, sorry about that, so plus 9/2 x, and then when you go 1/2 minus 3, well, notice 3 is 6 over 2, so you go 1 minus 6, which is -5 all over 2. And now we'll use this function right here to take our derivative. So we go g prime of x we're going to use the power rule, but we can pull out those constants. So 3 times the derivative with respect to x of x to the 6th minus 2 times the derivative of x to the negative 1 plus 9 halves times the derivative of x to the negative 5 halves. So what does all that equal? Well, this isn't too bad. We get 3, and then we'll go 6x to the 6 minus 1, close that one off, minus 2, and then we'll get negative 1x to the negative 1 minus 1. All we're doing is just applying that power rule every single time, and then plus 9 halves, and we'll get negative 5 halves x to the negative 5 halves minus 1, and close it off. And so at the end of the day, what do we have? This is g prime of x, and we'll kind of simplify all this all in one shot. 3 times 6 is 18. X to the 6 minus 1 makes x to the 5th. Okay, doing a couple algebra steps all at once. The next one, when you take negative 2 times negative 1, that makes plus 2. But notice that this thing is going to be x to the negative 2, meaning that needs to appear in the denominator as an x squared. So you get plus 2 on top, and then an over x squared. In a similar manner, we'll talk about this one. Notice negative 5 halves minus 1, that makes x to the negative 7 halves. Okay, so we have x to the negative 7 halves. What does that mean? Well, it means we're going to have this thing appear in the denominator, and you're going to have a square root because of the half power, and then you're going to raise it to the 7th. So this thing becomes, and notice we have a plus 9 halves minus a 5 times 9 halves minus a times negative 5 halves, I should say. And so we have 45 over 4, and then we get that square root of x to the 7th appearing in the denominator. And that's your final answer. Okay, and just like the other case, we had our final answer right there. Okay. Hopefully that makes sense in the power rule, because what we're going to do is we're going to expand that notion to the product rule coming up here soon enough. But first, let's take a look. One problem that gives some people trouble is making that connection between tangent lines and derivatives. So find the equation of a tangent line to the curve f of x equals 2x to the 7th minus 6 square root of x plus 5x at x equals 1. How do we do this? Well, in order to find the equation of a line, just any line, I'd say the easiest way to go about it is y minus y1 equals m times x minus x1, where x1, y1 is a point on the curve, and, or point on, I should say, I wrote curve because I'm thinking of what we're about to do here. A point on the line, and m is the slope. Well, there's some nice relationships here. We're at x equals 1. So what that tells us is we have 1 going in as the x value. How do we get the y? Well, we plug in 1 in for that x. So it'd be 1 comma f of 1, which we can figure out soon enough. So that, and then the other thing, how do we get the slope? Well, the slope, remember, the derivative at that point should tell you the slope of the tangent line. So this equation is y minus, instead of y1, we can change that to f of 1, whatever that might become, equals, m is now f prime of 1, and then we have x minus 1 in this case, since we're looking for that tangent line at x equals 1. Okay, so that's hunky-dory. Where do we go from here? Well, in order to do this, we actually have options. We can find f of 1 first, or we can try and find f prime of 1. If we try and find f prime of 1, what we'll need to do is we'll need to take the derivative first. So take the derivative of the function. So that should be 2 times the derivative of x to the 7th minus 6 times the derivative of, now I'm going to write that all in one shot. This is x to the 1/2 power because you have the square root of x, and then plus 5 times the derivative, and an easier way for us to see this is just x to the 1st power. Okay, so that means our derivative is 2 times 7x to the 7 minus 1 minus 6 times 1/2 x to the 1/2 minus 1 plus 5 times 1 times x to the 1 minus 1. Well, notice, what does all this equal? We get f prime of x equals 14x to the 6th minus, this becomes x to the negative 1/2, so you get 3 on top, and then the square root of x goes down below. And then notice this becomes x to the 0, and x to the 0 is just 1, so this is plus 5. Alright, so if we're trying to find f prime of 1, what do? Well, that would be 14 times 1 to the 6th minus 3 over the square root of 1, and then plus 5. So notice that's 14 minus 3, which is 11, plus 5 is 16. Okay. In a similar manner, we can find f of 1 from the original function. Okay, our original function is right up here. Just plug in 1 for all that, so you get 2 times 1 to the 7th minus 6 times the square root of 1 plus 5 times 1. So notice it'll be 2 minus 6 and then plus 5. So 2 minus 6 is negative 4, plus 5 should equal 1. Okay, that doesn't happen all the time, but we kind of lucked out here. So now we find our equation of our tangent line. It goes y minus y1. Well, our f of 1 value is 1. Equals m, which is given by f prime of 1, which we found f prime of 1 is 16, times x minus 1. And there's our equation for our tangent line. Okay, so a little bit more to do with derivatives is these product rules. How do we actually work that? Well, recall, and I'll shorthand this a little bit, you saw it on the very front. If I have two functions f and g, then we know the derivative is f prime of g plus f and then g prime. Okay, that's just a shorthand notation, but that way we have something to remember it by. Now, if we're taking a look at q of x, we have two functions. Remember, the 7 is just a constant. Okay, so we don't even have to worry about the 7. So when we calculate q prime of x, as long as we pull the 7 out front all the way, we're good to go. Now, we'll have the derivative of the first function. Doesn't always have to be the first, but it's easier to work that way, times the second function, tangent of x. Oops, got a little too excited with that extra parentheses there. And then plus, we have the derivative of our second function is going to be involved in this next bit. So x cubed times the derivative of our second function, which is tangent of x. Okay, so where do we go from here? Well, this makes 7. And we talked about the power rule. Hopefully we're getting a little bit more proficient at it. So the derivative of that x cubed is going to be 3x squared. It goes 3x to the 3 minus 1. 3 minus 1 is 2, so that's where you get that from. So 3x squared tangent of x plus, now x cubed, what's the derivative of tangent of x? Well, if you remember from that chart in the beginning, that's secant squared of x. And that is a fine final answer. If you want to get fancy with it, you can distribute the 7, so you get 21x squared tangent of x plus x cubed, 7x cubed, sorry, need to distribute that 7. 7x cubed secant squared of x. Okay. Moving forward to this next one, it's a little bit trickier because notice we don't just have 2. We have 1, We have 2 functions. We have 3. So there's a product of 3 functions. And how can we tell that? Always, we're looking for, if our variable's in here, how many times do you see that appear, essentially? That's all you're kind of focusing on. Now, it does get trickier when we have functions inside of functions. But so what I'll do is I'll rewrite this. I'll rewrite it as x e to the x, all in parentheses, times cosecant of x. So now what we'll do is we'll call this our first function and this our second function, and we'll kind of deal with it as we go, just trying to write it in terms of we're going to take the derivative. So that means we take the derivative of the first function, which is x e to the x, times our cosecant of x, and then plus our first function, so that's x e to the x, times the derivative of our second function. So since this is a product of 3, I wanted to try and illustrate here how we can keep on going with the product rule. Notice, so this means when we take this derivative, we have a product of 2 functions. So we're going to have derivative with respect to x of x times e to the x plus x times the derivative of e to the x, and all that's times cosecant of x. Now if you wanted to hop right to it and start taking derivatives, that's fine. I'm going to actually leave in the derivatives because I want to try and illustrate one extra point here. So what happens when we kind of move on down the line? Notice the cosecant x goes to each part. So this whole thing, if we were to write out the derivatives, notice it goes derivative of the first function times the second function and the third function, plus the first function times the derivative of the second function, and then times the third function, and then plus the first function times the second function times the derivative of the third function. So at the end of the day, here's what happens. I'll write it up at the top. If you have the derivative of 3 functions, f, g, and h, that equals f prime times g times h plus f times g prime times h plus f times g times h prime. So notice it's just the product rule extended a little bit further. You're just moving the derivative along the way. That's all there is to it. It happens, it works every time. You can extend this product rule to 4 functions, product of 4 functions, 5 functions, 6 functions. You name the number, it'll always work for you. So now it's derivative time. Remember, this first one is x to the first power, so you bring that 1 down and you get x to the 1 minus 1. So that just becomes 1 x to the 0, and x to the 0 is 1, so this whole thing is just 1. And then we have e to the x cosecant of x. And so all this is r prime of x. Plus our second one, derivative of e to the x is just e to the x, so you get x e to the x cosecant of x, and then last but certainly not least, you get x e to the x, and the derivative of cosecant of x is negative cosecant of x cotangent of x. That's one of our trig functions that we need to know soon enough, or if not, know sine and cosine, and I'll kind of show you how to work with those a little bit later. So our function, if we tried to simplify it, you get e to the x cosecant x, and we can factor that out if you notice of each of these terms. So you have an e to the x cosecant x here, an e to the x cosecant of x here, and an e to the x, even though it doesn't look like it, you have a cosecant of x there. So what are we left with? So we have 1 plus x, and then we have a minus symbol that needs to go right out in front. So this goes minus x, and then it goes cotangent x. And ta-da, we're done. Okay, so that's the product rule, kind of giving you a grips on that and how we can extend it even further. One other thing, you can kind of go even more abstract if you have functions in general. So say we wanted to find f prime of pi if g of x equals 2f of x cosine x and g prime of pi equals 7. Well, in order to do these types of problems, notice you see a prime involved, so we're going to need to take a derivative. So if we calculate g prime of x, notice that would equal, we can factor out the 2, take the derivative of the first function, which is going to be f of x. So derivative of f of x times cosine of x plus the function f of x times the derivative of cosine of x. So what do we get at the end of the day? Well, we get g prime of x equals 2 times derivative of f of x. You can leave it that way, or you can write it as f prime of x. That works just as well. And then we have cosine of x, and then plus f of x, derivative of cosine is negative sine of x. Okay, so now if you wanted g prime of pi, here's all you need to do. You get 2, get f prime of pi. Oh, I notice that's what we're looking for, the f prime of pi. Cosine of pi plus f of pi, which looks kind of scary because we don't have any information, and then negative sine of pi. Notice I'm not even simplifying this right now, just because we can kind of get towards the answer that way. Now, in case you do not know what happens here, this is the unit circle. Don't let your eyes fool you. That is a perfect circle. You have angle 0, pi over 2, pi, 3 pi over 2, then 2 pi back over there. The circle's equation is x squared plus y squared equals 1. That tells you some information. You have the point right here. This is going to be the point 1, 0. This point right here will be the point 0, 1. This point right here will be the point negative 1, 0. And this point down below will be 0, negative 1. And the other piece of information that's useful, you have x equal to cosine of theta, where theta is this angle kind of going around here in this direction, and it continues to go in that direction counterclockwise. And so y equals sine of theta. So anytime you want sine of theta, you just look at the y value. Well, so I'm highlighting the point even darker here. Negative 1, 0, that's the pi angle that we're looking for. So we can figure out cosine of pi and sine of pi. So g prime of pi, if you recall, is 7. That comes from up top. So you get 7 equals 2 times the quantity f prime of pi, which is what we're going to be looking for, cosine of pi. So that should be the x value on this unit circle. Notice the x value is negative 1, and this is your y value. So you get this times negative 1 plus f of pi times, well, sine of pi, so we have a negative symbol there. That's not going to make much of a difference because sine of pi is 0, because that's our y value corresponding to there. So at the end of the day, what do we have? Well, we can divide by negative 2 on both sides, and so we get negative 7 over 2 equals f prime of pi as our final answer. So we came up with an answer without even needing to know what the function is. Most people panic because they don't know what f is. You don't need it in this case. So, and that's what we try and build, is some abstract thinking there. Moving forward, on to the quotient rule. Now, just a reminder real quick, shorthand notation here. If you have f over g, first thing you do when you take the derivative, you go g squared, and then you take f prime times g, and then you subtract f times g prime. So similar to the product rule on top, except you have a minus symbol in between them, and so it does make a difference which one you have where. The denominator appears as the derivative after the minus sign. So keep that in mind when it comes down to it. Another way, as I mentioned before, some people do the low d high minus high d low. That works as well. Whatever gets you to memorize this or have a good comfort level with this stuff, that's awesome. So notice we have two functions. Our functions are x to the 7th and then natural log of x plus 9. Quotient rule, usually that comes about pretty nicely in terms of you can determine what's your f and what's your g real quick. So the first thing I like to do personally, and we can always make our decisions in terms of what we want to do first, but is to square the bottom, because that's pretty straightforward. And so then we're going to take the derivative of the top function, which we'll write as derivative of x to the 7th, times the bottom function, which is natural log of x plus 9. Notice how the whole denominator is in parentheses, because all that's times that derivative. That's important as well. So if you have multiple terms in the denominator, make sure to put that parentheses there. So minus the numerator times the derivative of the denominator, which is natural log of x, once again, plus 9. Okay, so what is all this business? Well, we have natural log of x plus 9, the quantity squared. Derivative of x to the 7th, that's the power rule. 7x to the 7 minus 1 power, the 7 minus 1 just equals 6. So 7x to the 6th times natural log of x plus 9. And then minus x to the 7th. What is the derivative of natural log of x? Well, it's 1 over x. And then the derivative of 9 is 0. Okay? So, moving forward from there, what do we get as our final answer? Well, let's write it in this spot. So we get p prime of x equals 7x to the 6th times natural log of x plus 9. X to the 7th times 1 over x is just x to the 6th, so minus x to the 6th all over natural log of x plus 9, the quantity squared. Now some people try and think that you can cancel off the natural log of x plus 9's here. You can't, because you don't have a natural log of x plus 9 in both terms. You need it where the x to the 6th is as well. So since you don't have that, you can't cross it off, and keep that in mind too when simplifying. So that's our simplified format. Not saying you had to do that. The previous answer would be just fine. So notice all these before we've been dealing with the derivative with respect to x. Notice now we have a t. So what do you think we'll take our derivative with respect to? Well, it's going to be t. And so that's the whole idea here, is just getting comfortable with the symbols. So same rules apply, though. You're going to square the bottom. Oh, I don't know why I wrote x. Sorry about that. Those should be t's. So 5t to the 11th minus 7t plus 3. Okay, so 5t to the 11th minus 7t plus 3, the quantity squared. And then now we take the derivative of the numerator, derivative of sine of t. So d dt now. Not talking about that spray that people use, but we're talking about derivative with respect to t. So times 5t to the 11th minus 7t plus 3, and minus sine of t times the derivative with respect to t of 5t to the 11th minus 7t plus 3. Alright. So what does this whole thing equal? Now I'm not going to simplify this one just because you all can do that from there. So we'll go 5t to the 11th minus 7t plus 3, the quantity squared. What's the derivative of sine of t? Well, that is cosine of t. Alright, alright. So times the 5t to the 11th minus 7t plus 3. And so we'll move a little bit quicker. If not, you can always slow me down. Just let me know. So sine of t, derivative of 5t to the 11th. Remember, 5 is a constant, so we're just worried about the t to the 11th. Use the power rule. That's 11t to the 10th power. So 5 times 11 makes 55. And then we have t to the 10th power. Minus 7t, remember that's t to the first power. So minus 7, and then t to the first power goes 1 times t to the 0. But t to the 0 is just 1, so that's 1 times 1, so minus 7 times 1 times 1 gives you 7. And the derivative of 3 is just 0, so we're left with that. And that is a good final answer right there. So now hopefully you see, if you're good with the power rule, you can make this stuff move even quicker, right? It just takes practice. That's the big thing there. Alright, so now for what can we do with the quotient rule? We can actually prove some of the results. Remember I mentioned the trig functions. You really don't need to have them all memorized as long as you know sine and cosine. So if you know what cotangent is, the derivative of cotangent, well, there's another way to write cotangent, and that is cosine over sine. So this is the derivative of cosine of x over sine of x. Okay. So now what do? Well, we can use our quotient rule. So we're left with a sine squared x, and then what happens in the numerator? Well, you take the derivative of the numerator, so derivative of cosine of x times sine of x minus the derivative, so we're going to be multiplying by the derivative of the denominator here in a second, but so you take cosine of x times the derivative of sine of x. Okay, so what does all this become? Well, derivative of cosine of x is negative sine of x, so you get negative sine of x times, that's a multiplication, times sine of x, and then minus cosine x. Derivative of sine of x is positive cosine x, so we'll just write cosine x, and all that is over sine squared. So what happens here? Well, we can factor out a negative 1 out of the numerator, so negative 1, I'll even write the 1, it's not necessary, but notice sine times sine makes sine squared. So sine squared x plus cosine x times cosine x, it makes cosine squared of x. So what happens here? Well, this is, if you recall, there's a trig identity, and I'll use theta up here. Sine squared theta plus cosine squared theta, always, and you can test it out with some numbers in your calculator and things like that. No matter what numbers you come up with, you always get equal to 1. So this whole thing equals negative 1 over sine squared of x. Well, what does that mean? Well, that means we can rewrite this as, if you don't like that, you can write it as negative 1 over sine x, the quantity squared. Notice I pulled the negative out in front because we want the whole thing to be negative. If we squared that, it would just be positive, so we got to be careful there. But 1 over sine of x is just the cosecant x. Okay, so this is negative cosecant x, and you could have done this a step earlier if need be. And so the whole thing equals negative cosecant squared of x. And that's pretty much how you prove all the trig functions other than sine and cosine. Those you do use limits and just use some angle formulas that you can work with. So, but at the end of the day, notice we just shown that the derivative of cotangent of x equals negative cosecant squared x. And what was the whole trick to it? All we used was the quotient rule. The same rules apply for showing the derivative of tangent x equals secant squared, showing the derivative of secant x equals secant x tangent x, and showing the derivative of cosecant x equals negative cosecant x cotangent x. They all come from the quotient rule as soon as you know derivatives of sine and cosine. So if you ever get nervous about it, you don't know them, well, just think back. As long as you can write them in terms of sine and cosine, you're in good shape. So last but not least, let's put this all together and try and calculate a derivative. So first things first, let's rewrite this function just to make it a little bit nicer. So you can write the first part as 7x to the, this is the 5/3 power, minus, we'll leave that alone, you have 4x e to the x, and then cosine x, and then plus 17, and then that's x to the negative 9/2 power. So when we try and calculate f prime of x, we're going to have a couple power rules, we're going to have a product rule, quotient rule, all sorts of fun stuff going on here. So derivative of the first one, so we'll just write 7 times the derivative of x to the 5/3, which we'll calculate in just a minute, minus, in the second one, we're going to use quotient rule first. So you see cosine squared times the derivative of 4x e to the x times cosine x minus 4x e to the x times the derivative of cosine x. And then plus 17 times the derivative of x to the negative 9/2. Alright, so where do we go from this point forward? Well, you get 7, and then this becomes 5/3 x to the 5/3 minus 1. Well, 5/3 minus 1, that's 5 minus 3 over 3, or 5/3 minus 3 over 3, I should say. So, and 5 minus 3 makes 2/3. So try and check that, make sure that works out. In the second bit, though, notice that this derivative is a product of two functions, along with the 4 sitting out there. So we have to use the product rule. So you get 4 times the derivative of x times e to the x. And this time it's a plus. Then we'll have x times the derivative of e to the x. And then all that's times cosine of x minus 4x e to the x, and the derivative of cosine of x is just negative sine of x. And all that is over cosine squared of x. Plus 17, you get x, oops, got a little ahead of myself there. So you're going to get negative 9/2. Pulling that down in front, x to the negative 9/2 minus 1, well that's negative 9/2 minus 2 over 2, so that makes negative 11 over 2. Okay, so what happens here? If we're to brush this up, not saying we have to all the way, other ways to write this, you can write this as 35 over 3 if need be. And once again, you do not have to do all this brushing up. It's just good for people to see, because sometimes you might look in the back of a book and see an answer different than your own. So I want you to be aware of what's going on there. So in the next part, what happens? We get 4 and then times e to the x plus x e to the x, because the derivative of e to the x is e to the x, and then times cosine of x minus a minus, because you have that minus sign sitting there. That's going to be plus 4x e to the x sine of x all over cosine squared x, and then 17 times 9, so that'd be, I believe that's 153, so negative 153 over 2, if I did that right. So otherwise just put 17 times 9, and then x to the negative 11/2. So notice that means negative means it's in the denominator. The half power tells you have a square root, and then it's x to the 11th, and you're all done. Oh, you can brush up the numerator if need be. It's not necessary, but some people like to do that, so that's up to you at the end of the day. Hopefully that makes sense in terms of these derivatives, and now you've seen one where, hey, we just take the derivative completely without knowing, is it power rule, is it product rule, what's going on. So you have to decipher all those together, and that's more realistic as to what might happen. If you have any other questions, please post them, and I'm happy to hear from you.